Hey there, everyone. Welcome to my channel. My name is Ryan Schul. This station or channel, whatever you want to call it, I guess it's the channel, is all about data science, machine learning, deep learning, artificial intelligence, and so on and so forth. So for today's topic, I want to talk about how we can analyze energy consumption in buildings all across New York City. Okay, so I live in New York City. I think this is pretty interesting for a variety of reasons. If we understand the energy use of buildings, we can monitor energy use, right? We can do energy audits, set up smart meters and sensors to assess how much energy each building is using. Is it efficient? Is it not efficient? Why is it efficient? How can it become more efficient? Things like this. And then we can understand ways to optimize HVACs, optimize the way lighting is controlled, right? With light sensors in certain rooms. If there's motion, then light comes on because there's somebody in the room. If there's no motion, then we probably don't need to burn energy and keep the light on, like in hallways and stairwells and in areas that don't get a lot of common use, things like this, right? And understand how we can do LED upgrades. Light emitting diodes are more efficient, right? Maybe use more efficient um, what they're called, fluorescent lights, things like this, right? There's all kinds of ways to improve the way that the building consumes energy and just manage the overall process better, right? So I have a few things in my notes to address these topics that we're going to take a look at today. You can check that out when you have a chance. I'm going to share all this code with you like all the other teaching sessions that I put together. I share the code with everybody so you can copy and paste this and run this in your own Jupyter environment or Spider, if you use the Spider IDE or whatever IDE you have, right? As long as it's Python, it should work just as well for you as it does for me. So let's get into it. I found this data set over here. I looked at a few. This one looked like it was kind of interesting. I'll take you through a quick peek at what this looks like here. This is all JSON data, right? Put up by New York City, and essentially I have my notes here. This is local law 84, started in 2009, LL 84, requires annual energy and water benchmarking data to be submitted by the owners of the building. So I live in Queens, New York. Everybody in Queens is subjected to this, the five boroughs, right? Brooklyn, Manhattan, Staten Island, and Bronx. They'll have to submit these metrics to the city of New York. So each property is identified with an EPA assessed property ID that contains one or more tax lots identified by one or more buildings, borough blocks and lot, BBL, borough blocks and lot. And we can look at this to understand energy efficiency ratings and get additional information from that. So this is still spinning. This is where the data comes from. I guess we can't really view it. It's kind of slow to load up, but that's fine. You'll see it in just a moment. So we go ahead and fetch this JSON and go ahead and parse it just using a couple simple tools like that, right? And we'll get the metadata, the view, and the columns, and convert columns into actual columns and rows into rows and map those together. So in the end, we get a nice looking data frame that essentially looks like this, right? We have 64,000 rows, 273 columns. It's always row, comma, column. You'll see this in Excel. You see the same thing in a Python data frame. So 64,169 rows and 273 columns, right? So the columns contain information like ID, created, metadata, updates, property name, property ID, and so on and so forth, right? The borough, the block number, address, and the five boroughs that's located in, so on and so forth, right? So here's all the data, 273 columns, pretty extensive and pretty rich data set overall, right? So it's almost too much information. I identified this as TMI, too much information. And I said maybe we should just focus on the following items like benchmarking building performance against similar structures, identify correlations between building characteristics, segment buildings into clusters for further analysis, detect trends and anomalies over time, and then build predictive models to forecast energy usage. So that's kind of the focus. As a general guideline, I don't know if I really do a deep dive into every single one of these, but that's the guideline that we're going to follow, or try to stay within those guardrails. Okay, so when you look at the print up all of the column names over here, so you have DF columns to list. We have a list of all the columns. So you can see that it's pretty extensive, 273. One thing that stuck out at me is we have a lot of objects. So we have int64 only 5 times, and we have all of these other objects. Everything is identified as an object, which is basically a string. But if you look close at the data, these aren't objects at all, right? This is a number, this is a number, this is a number. These are all numbers over here, numbers, numbers, numbers. So those numbers everywhere is at least 55 to 60 columns with numbers, but the city of New York identifies these as strings, right? So that stuck out at me right at the beginning. I thought, like, how can I know what is an actual number and what is actually a string? Because some are true strings and some are just labeled as strings, like this over here, but it could be an actual number, right? So if you're looking at, I think this is British thermal units, and British thermal units consumed per square foot, that's going to be a number, right? That's no way that that is a string. So the first thing I thought of, and this is kind of brilliant actually, is to look at the conversion ratio. If I can try to convert those from a string over here into a numeric, and we get a pretty high conversion rate, like over 90%, I'm going to call those actual numbers and not strings, right? So I think the city of New York, in all of their infinite wisdom, mislabeled these, or maybe they didn't understand what was going on, or maybe they just didn't care. I don't know. But if the conversion ratio is higher than 90%, I am going to go ahead and append those numeric columns into this list and then convert the list into an actual data frame with actual numbers. So that's the methodology here that I followed to find out what was an actual number and what was labeled as a string but should have been a number, right? So that's why I got this down here. Okay, just so you have some insight as to why I'm doing that, right? And then we can see right here columns that are mostly numeric, right? Based on this logic over here, conversion ratio, if we can convert at least 90% to numbers, this is going to be relabeled as a number and not a string, right? So columns that are mostly numeric, these are the ones I came up with. I think it's like 55 or 60 of these. Yeah, down here. Okay, so we can see 55 numeric columns. There was the original number of rows that we started with, so 64,000 rows, and we can convert every single one of those into numerical columns. And if there's an error during the conversion, we coerce that into an actual number. Okay, so some of these might trigger an error, but we want to handle that gracefully by converting these quasi strings, which is not a real string, into an actual number, right? We want to fix this mistake that the city of New York created. That's why we do that. So I'm just grabbing 1,000 records to make this run a little bit faster, because if we did this for all 64,000, that would take quite a while. We can do it magnitudes times faster if we just do 1,000 records. Now, if you want to go get all 64,000, by all means, go for it. It's going to take a little while to do that. I didn't want to wait for that process to finish off, so I just took a subset of the whole data set. So I'm taking the head of the original data frame and just using the first 1,000 records. So that's why I got to that. Okay, so if you need everything, go for it. Go convert everything. If you don't need anything, if you don't need everything and you just want to look at a subset, then just stick with this code that I have. Okay, so then we have here filtering out columns containing emission or electricity. So any column that has the word emission or electricity, I'm going to take these out because there's a very high correlation between that terminology and the site energy use. So the site energy use is how much energy each building is going to use. I want to understand the metrics of the energy usage of all the buildings, but if I do, or if I include this in my analysis, emissions or electricity, both of these are essentially proxies for this right here. So you have a very high correlation between these terms, but you're not going to see what really drives the site energy use. It's not going to be emissions. That is what maybe Con Ed or some energy producer will create some emissions, right, to produce the energy that's consumed by the building. So these things are almost exactly the same, right? This is emissions or energy use or electricity consumption are all proxies for the same thing, right? I want to be able to do an analysis to say, if I remove these, what is the target variable going to be impacted by when all of the very high correlated features are removed, right? Because I don't want to say high emissions, high electricity, and high site energy use. Those are all exactly the same thing, or essentially the same thing, right? I want to remove those. So if I remove those, I get those down to about 37 columns. So this is how we get originally from, I think, 273 columns we had, quite a bit, down to 37 that are mostly useful and relevant for this analysis without getting into all the superfluous extra unnecessary kinds of features out there in the original data frame, right? Remember, those 273 is pretty extensive TMI, too much information. We have to reduce this into a subset that's more user-friendly and more consumable and more easy to manage, right? So once I do that, I can go ahead and start my feature importance exercise. So feature importance basically lets me assign a target variable right here. I want to look at site energy use. This is how much energy each building in New York City is using. And then I can see which kind of factors influence the site energy use, right? So once we remove energy and emissions and get those things out of there, because essentially that's the same thing. You can see a very high correlation, but that's not helping me understand what really impacts the energy consumption of that building, right? Because it's the same thing. Once I remove those, I can see and source energy use is going to be highly relevant to the building's consumption of energy. But you also see some other interesting things shake out here, right? So largest property type building, gross floor area. So it's pretty obvious that the bigger the building, the more the square footage, the larger the structure, the more energy it's going to consume, right? If you have a behemoth-sized building that's absolutely massive, it's going to consume more energy than a small warehouse or a tiny school or something like that, right? So you do see a correlation between the gross area size of the building and energy consumed. That totally makes sense. Building and parking, square footage again, square footage is a big factor, square footage again, square footage. So in all these cases, in the top 5 or 6 cases, the size of the building is highly correlated to the energy that the building consumes, right? So that is pretty obvious. Property ID actually had a relationship to the target variable. Again, the target is site energy use. So that's kind of interesting. We could remove that, just leave it. It's a pretty small percentage. Year built actually has some impact, but it's pretty tiny. And the national median site has a small relationship to the amount of energy that the building uses, but again, it's pretty tiny. So the big ones here, you can see in descending order what they're source energy use, largest property use, square footage, and that makes sense, right? The bigger the building, the more energy. So there you go. We proved that. What else? So 4 features were removed prior to the feature importance exercise. Actually, let me get rid of this because all of those that was my original notes. Let me cut that out because that is going up because we actually removed quite a few. We ended up keeping 37 features, but we started with 55. But remember, we got rid of anything that has emissions or electricity in the field name. So if we look over here for some examples, emissions, energy. So that something like that would be gone. Emission. What else? Electricity use, right? So if I'm trying to measure electricity use, I don't want different versions of electricity use to impact this analysis, right? I just want it to be more cut and dried and more relevant to non-high correlated features, right? If you're trying to measure somebody's height in terms of what height in terms of centimeters, inches, feet, and meters, these are all the same things. You would just use one metric. You wouldn't use 4, right? That doesn't make sense to use 4, so I'm getting rid of some of these that are essentially the same feature, right? So I did a PCA, principal component analysis, type of exercise to see what kind of features have a high impact on the target variable. The target is what we're trying to measure, right? So site energy use, this is going to be the Y variable or the target, and all the other features are the independent features, and we're trying to see which ones have the biggest impact on the site energy use, and you can see that down here. And again, I plotted everything in descending order. So energy use, occupancy of the building. So that's interesting, right? The bigger the building, the more occupants. Year built and number of buildings. active energy meters, latitude, longitude actually has an impact, right? National median site, and a couple other metrics down here. So I thought that was pretty interesting. Then they started to plot these things, right? So I came up with a couple different ways to look at this. This is the box plot of EUI. So the box plot will show you the outliers. So here's one outlier. This is interesting. I don't know if this is just an anomaly or data quality issue, but you see EUI very high, 561,000. But most of these are much smaller, like 15,000, 8,000, 10,000. Even these are some bigger EUI numbers over here. And I like these plotly charts because you can zoom in and look at all the details behind the chart, right? And you can see all the metrics here, the max, the min, upper, lower, and the quartiles, Q1 through Q2, Q3, upper, top, and the lower, and things like that. So that's pretty cool too. Let me see, can I go ahead and reset that? I think so, yeah, okay. Okay, so box plots basically show us the outliers here and then how everything is tied up over here, or the dispersion, right, of all of the data points here. So this box plot I thought was interesting. We have the 5 boroughs here, and again, the dispersion. So Queens has pretty much the same data points around the same sort of structure, around the same frame. It kind of looks like a violin. That's why it's called a violin plot. And you see the quartiles, right? So the median, mean, upper, lower, min, max, things like that. And you see for all the boroughs, so Bronx, Manhattan, Brooklyn. There's one significant outlier here in, oh, this one doesn't even have an ID associated with it, or a borough associated with it. So I think that is a data quality issue. You see Staten Island down here. These are all pretty tightly bound together. And this, I think, is a data quality issue over here. So so Energy Star by borough. So again, we see the boroughs over here. This, I think, is just mislabeled. It doesn't have a label, right? But we can see Queens, Bronx, Manhattan, Brooklyn, Staten Island. Then we have the postal code, or the it's called the neighborhood tabulation area. And again, we can get these box plots, these violin plots. It's kind of like a box plot. Again, it shows you dispersion, all the outliers. And I think this is pretty interesting by zip code. These are the top, what is it, top 10 zip codes around the New York City area in terms of EUI. Again, this is energy consumption by building. I don't need that right there. Cut that out. And then we have clustering. With K-means clustering. So I'm looking at the clusters of EUI usage. Again, this is energy usage, and you see clusters, 4 clusters here, 0 through 3. We always start at 0, right, and go 1, 2, 3. So these are 4 clusters here, and we see a lot of cluster 2 lower here on the building square footage relative to the EUI. This is the energy usage. And then we have another type of clustering algorithm down here. For DBSCAN. So it's just a different type of clustering methodology, right? And we have DBSCAN, which will look at the density of clusters. Again, we have basically 2 outcomes right here. And let me finish, almost done here. We have 2 types of clusters. We have the cluster 0 and cluster 1. That's all we're getting here. And you can see the density really is in 0 clusters. So everything is kind of congregated right here around this. And with the density outliers, we'll have this on the y-axis going up, and on the x-axis over here. And again, this one might be a data quality issue or just a complete mistake. We have calculated building size 300 or 3.8 million square feet. I think that's what that is, 3.8 million. So that's very big. But maybe that's actually like a real building. That would be a huge building, but maybe that is true. So that one might be a talking point right there. Here's 2 million square feet. And then this is a very high energy usage right here. For a building, it's only 2,000 square feet. You have a EUI of over 1,100. That seems like might be a mistake. So anything that comes out with a DBSCAN type of analysis might be a good talking point. Like, is this actually a mistake, or is this correct? Is this a mistake or correct? Is this a mistake or correct? If it's correct, we should probably look into this. Why is a small building of 2,000 square feet using 1,100 EUI units? That's a huge consumer of energy, and this is just a massive science building. So if that's correct, that's correct. If it's not, we should fix the data. Now, of all the charts, I think this one might be the most interesting. We have energy consumption by type of building. So supermarkets are actually the #1 consumer of energy in the New York City area. I did not know that, so that is very enlightening. Laboratories are #2 and hospitals are #3. Now, hospital makes sense to me. It's always on, 24/7. The lights are on, the AC is on, the heat is on in the winter, AC in the summer. Lots of power for all of the medical equipment that the hospital needs to conduct its business, right? And that totally makes sense. And self-storage facility, that makes sense that would be on the lower end, the lowest end of the spectrum. Primary property type transportation, train station, non-refrigerated warehouse, and then self-storage coming in as the least consumer of energy. So that is pretty interesting. That makes sense to me. I didn't actually know that offhand, but that makes sense now that I see the analysis. So I think that was the most interesting chart that I found here. Residual analysis, again, looking at actual versus predicted energy use and plotting all of these. I thought that was interesting. And then normalizing the metrics and coming up with a composite score here. So the composite score is something that's I created, but I think this totally makes sense. So you don't get this in the data. You have to kind of like fabricate this yourself. But if you look at the EUI, again, this is energy consumption. And then the minimum and the maximum, right? And getting an energy composite score and then the energy star score. So these energy stars get up to 100, right? It's from 0 to 100. You see it's all around New York City. I think this is very interesting because you see the property name, the composite score, and then the energy star score. This is the top 25 buildings. And here I got the top 25 worst. So this is the top 25 best. Right here, this is the top 25 worst. So this is the tail. Right, I've got the tail and 25 and the head and the top 25. So you can see composite score is pretty low down here, down to 20%, and this is 1/2 of 1% for a storage garage. And then the energy source score is basically 1.0, 2.0, right? So you want higher is better. You want 100 or probably at least 90. My building where I live has 90. These guys are getting 100. That's pretty amazing, but they're doing a great job with energy utilization and efficiency. These guys down here kind of suck, right? And then what at the end? Oh yeah, and I thought this chart was very interesting too, with the darker colors having the bigger numbers, right? So composite score 0.99, 0.99 composite score, and then you have the longitude and latitude, and this all comes from that data set that you saw at the beginning with 273 columns. They give you the latitude, they give you the longitude. We create a composite score and match it against the energy star score, which you get right here. So you get 100. And this pretty much corresponds almost perfectly to the composite score. So higher is better, right? You want to be 100%. Anything above 90%, in my opinion, is fine. 90% efficiency up to 100%. That's the best you can get, right? And then this is a plot of all the latitude and longitude coordinates all around New York City with the building address. Usually, sometimes you get the building name and then the energy score, right? So darker is better, lighter is worse. These guys have a score of 0.46 energy efficiency, so not even half. This is pretty decent, 96% on. This is pretty close to 99.3%, and this guy's pretty close to 99%. Okay, so I thought that was pretty interesting. Energy consumption around New York City. And that's it. That's my findings. That's my analysis. That's my takeaway. So hopefully this was enlightening to you. I'll cut that out. I only need that right there. And I have some notes in conclusion here. Dataset doesn't provide real-time sensor data. That would be nice. We could do really optimization of energy utilization. If we had this real-time access to real-time data, we don't have that. So we're kind of limited in that kind of analysis. But then if you do get that, you could do automation controls, LED lights, motion sensors, HVAC optimization, things like that. So there's a lot of ways to improve how buildings utilize energy, utilizing consume energy, right? And then try to make the process more automated. Any kind of controls should be automated. We could do predictive analytics to see even what time of the day or what day of the week energy use is going to spike up or dip down. It can pretty much guarantee during rush hour When people getting up in the morning between 7 a.m. and 9 a.m., it's go time. A lot of people are getting out of bed, taking showers, running the oven, running the lights, maybe running some more utilities than you would normally. Overnight, it's going to dip down, right? And in the evening time when people come home, the numbers are going to spike up again. So around rush hour, you would see a big spike up in the morning, a big spike up in the evening, and nighttime it's going to dip down right when everybody's sleeping, or most people are sleeping unless you work third shift. And then that's going to be the Monday through Friday schedule. The Saturday and Sunday schedule is going to be slightly different because it's the weekend. People have different routines on the weekend than they have on the weekdays. So you would see that type of analysis. If we had that data, I can guarantee that's how it's going to look. We don't have the data, so I can't really do the analysis, but I've seen that in the past. I worked for 2 energy companies before, and that's very, very, very common to see those types of trends. So that's it. Energy consumption in New York City buildings, and we're using Python for the analysis. That's it, guys. I'm going to wrap it up here, and I'll see you in the next video. Goodbye.